Hello and good evening. Thank you for tuning in to my channel. This is the last video I created. It's called the 74HC595 shift register. It's part 16 and it's in my PIC10F200 playlist. Please look for the playlist on my channel. This is about how many videos I currently have. The cover way back when, the thumbnail main screen I chose for my PIC10F200 projects looks like this. So it will be one of these videos. And just to recap a little bit, this shift register video is like an evolving project. I wasn't sure where things were headed originally, but I got some of these shift registers in the mail. I wanted to play around with them, but I knew to use them I'd have to have many debounced switches to give it a test, so I built up a debounced multi-switch digital module in preparation for my shift registers. In fact, while I waited for them to come in the mail, I built this monstrosity here, but it works really well. So I made this, and I'm basically controlling a shift register. Here's the shift register with my fingers, with push buttons, with output signals, lows and highs. If you watch this video, maybe not perfectly, but it explains the signals and the pins that are manipulated on the 74HC595 shift register. And I don't really recap that very well in my PIC10F200 videos where I'm controlling the shift register. So that might be handy to watch if you really want to know what I'm talking about in this video. Okay, sorry, I'm long-winded, but that should bring things up to speed with what I'm doing here. Once again, I'm not an expert. I'm just a guy trying to figure stuff out on my own. This video contains some code I developed to spit out a number onto this type of shift register. So now I'm going to clean up my code as best I can and get it doing something different. I'm going to try and add a counter to this code here. So voila, I've brought up the code from my last project, from my last video, and I'll make the changes while I'm recording. So I'm going to document the process. This commented out code is from a Blink program. I never needed it in this program, so I'll delete all that jazz. Now, even when I started this program, I intended for this counter, or this equate C1 to store a counter value. I just never included the applicable code to do that. So I'll do that now. And I will delete this. All this did was put a fixed literal value, a constant value, into that counter. Well, we want it to count. We don't want a fixed number, so I will just delete. And in the initialization portion of my code, I will clear the counter C1 just to be sure, especially because currently I'm using the mclear pin. If I reset the chip while it's operating, it'll just bring this counter storage back to 0. So let's start out with a cleared C1 register that I specified as an equate. And the point is to PIC10F C1. How embarrassing. Now I have a problem. Now my code starts, and it starts counting at 1. I want it to start counting at 0. So how do I fix that problem? I mean, I could take it out of here. I'll just cut this, and I could put it here. So after all the bits are tested, then it increments the counter, and then it goes back up to the loop, which currently has no code in it. Okay, you didn't see it because I did it off camera when I paused for a moment, but I clean and built the program and uploaded it into my PIC10F200, and it works. So all those changes were a success. That wasn't very hard, but still have to check all the time to make sure I got it right. So the next thing I wanted to do to clean up my code was to do something about this delay routine. You can't see it, but oh, never mind. I cut off the end directive off the screen. The recording window doesn't catch it. What I wanted to do was to add a different delay routine. And this delay routine that I'm currently using uses counters for inner and outer loop. So for now, I'll just comment them out. Likewise with all this. Quick and sloppy. And I will paste in something I borrowed from another program. And this doesn't set up equate files. It just uses file numbers. But this is a problem because it's actually using my counter value. So maybe I'll just change my counter value to 14. I'll change the code so it just calls it delay, because my existing code uses the label delay. So I'll have to clean and build and upload and see if this works. It should. Silly me. Lab says that's okay. Nope, this was wrong. I didn't include the whole delay subroutine. I forgot the part where I load up all of these files with a value of decimal 5. So now it's complete. This must be very confusing to the viewer watching. I told you I'm not an expert. What can I say? That's better. Alright, so I clean and builded, and then I uploaded the code into my PIC10F200 chip. And it works. It's successful. But with all of these delays here and here and here, and the length of the delay, the counting of my numbers is about 2 minutes between each digit count. That's how long the delay is. So that's not really ideal. I realize there is a simple mathematical equation or formula for determining a delay routine, and you take into consideration the speed of the internal oscillator of the chip. I know that. I know that that's all out there. And maybe you would call me lazy for not wanting to look it up. But I'm going to ignore that that exists, and I'm just going to use the trial and error method for getting an appropriate delay time. So for starters, let's just change decimal 5 to decimal 1, clean and build, and then upload. And it'd be nice if I showed you what was going on my breadboard setup. And upload. Success. Okay, so insert first video here, and I'm going to show you that the shift register cannot handle this length of delay. Now this is too fast. It's going through iterating through the code way too fast. And I could try to put that into words, but if you take a look at what's going on my setup, it's all screwy, if that's an acceptable word. Take a look.
Mamma mia. I don't think this is supposed to be working like this. These LEDs are blinking and these ones are just on. So something's not right.
Okay, so that didn't work. Let's try adding a 2. I'll show you that on camera too.
Okay, so this is video 2, and I added the value 2 into that delay routine, and now things are just happening way too slowly.
So this whole delay routine just isn't working the way I'd like it to. So I'm still using the trial and error method, and I think that maybe I will get rid of one of these counter file registers. Can I do that by just commenting stuff out? And maybe I'll give it a value like 50, because now I'm only using 2 counters. I'll see if that works. Okay, 50 is a bit slow. Let's go with 25. 25 is really nice, and I'm going to show you that. Have a look.
Okay, I'll just hit the M clear. Ooh, that's really nice. I like that.
Okay, so I guess I can get rid of all this jazz. And let's pretend I never wrote that. Let's move this counter back to 12. And I'll just get rid of these commented out lines. These comments don't make a whole lot of sense because I borrowed this from another code. I guess somebody figured that 1/8 of a second and the number of loops. Yeah, somebody understood this better than I did. Alright, so this code could use a little more cleaning up. And I won't re-explain the code. I did that in my last video. But it tends to repeat itself every bit test of the C1 storage counter. So I was thinking that all of these instructions could be put into a separate subroutine instead of writing them as many times, especially considering we're using a PIC10F200, which has limited program memory to begin with. What this does is it controls the serial input pin on the shift register. So if I'm going to make a separate subroutine for this code, I might call it something like the serial routine. Will it? Because this bit test file skip if clear relies upon the next line of code being directly below it. So I can't have that line of code shoved into a separate subroutine. It's got to be below this BTFSC. See, I do things too quickly before I think them through sometimes. I don't know if you ever do that or that's just me. So this can't be in the subroutine. It's got to go with that code. So it has to go with that. So I clean and builded and uploaded, and it didn't like that. It's not working. So this separate serial subroutine is not working, at least the way I set it up. And I have no idea why. So thank goodness for the Control Z keyboard undo thing because I brought it back to the way it was before I created that serial routine. Now, why didn't it work? Was it my coding skills? Or is there some kind of rule about subroutines within subroutines? Maybe you know. Okay. This is something I was thinking about. So the shift register. More specifically, this shift register here. Maybe I should check the data sheet. But my question is, how quickly, at what rate, can this shift register take in new bits of information? Okay, so I looked up the data sheet of the shift register, the 74HC595. And I don't know if I'm looking at the exact correct information as to how quickly the shift register can accept serial bits of information. But here's something that remarks on the speed of the unit or the clock frequency. The min at 2 volts, I guess the voltage matters. I don't know how that works. 5 max for megahertz. And I guess if you're running at 6 volts, 29 megahertz. I suppose I should study the chip more closely. Yeah, but I'm going to have to say I'm ignorant. I mean, even if these are the specifications for the clock frequency, how does that relate to the timing here of the number of clock cycles? Is that a direct relationship to what's going on here, or like, I don't know, I can only guess. I need a lesson. Here's the switching characteristics, talking about nanoseconds. So I know the answer's in here somewhere. I'm either not smart enough or I'm too lazy to figure that one out. So I will go back to my trial and error method, and let's set this up for, I don't know, 5. Yeah, sure, 5. Now that I only have 2 loop counters. Okay, this video is going to be more and more challenging to make, but I'll switch over to another clip of what that looks like.
Okay, this is with 2 counters, and I set the decimal number there back to 5. I've got a need for speed, so let's go faster.
Well, let's just go as fast as I can, down to 1. Alright, 1 doesn't work. I didn't even show it on camera. But 2 works, and I'll show you what that looks like.
Okay, here's the decimal value at 2.
So this project is complicated enough, so I might just cut it short and create the video. I still have a few other things I'd like to try. So the next following video I'm going to make hopefully shows that.